Welcome back class. So last time we learned about the equivalent circuit of a transformer, and we learned that we can actually make the equivalent circuit of the transformer using the primary winding resistance, secondary winding. The leakage reactance we can model in terms of the inductor, and second same as the secondary leakage reactance, the core excitation current model, which constitutes of the hysteresis and core losses, and the magnetization current component, okay, which is we model as the inductor. Then we learned that basically this is primary side, this is secondary side, and we learned that how we can actually convert the primary side circuit, like we are looking from the primary side, okay. So the primary side circuit, which we actually look actually from this end, so that is basically is equal to a square times the secondary side impedance, which is this, okay. So we can model the two circuits. The first one, the transformer model, refer to the primary voltage level, okay. So referring to the primary voltage level, so this impedance was modeled by a square, right? And we know that the ratio of the primary and secondary voltage is turn ratio, right? So when we are making primary side model, so the secondary side voltage will also be converted to the primary side voltage, right? Which is basically A times of Bs, okay, because we are modeling towards the primary side. And similarly, if we are going vice versa, okay, like we are trying to model the transformer model refer to the secondary side. So secondary side referring means now we are making this complete primary side impedance towards the secondary side. So when we are doing this, so basically impedance looking from this end, that will be the primary side impedance divided by A square. So this whole impedance will be divided by A square. And now looking at the same formula, the ratio of Vp over Vs is A. So now we are actually converting our primary side voltage towards the secondary side voltage, sorry, Vs. So the secondary side voltage basically it will become Vp over A, right? So that will be actually our primary side voltage referring to the secondary side, okay. So these were the two models which we have learned last time. And the main component here, okay, like we have the series components, and then we have the excitation branch. So basically excitation branch is adding the making the circuit kind of a complex, okay. The other reason is if we compare like this primary current and secondary current, okay, like this is my primary current, this is like the primary current, and this is our secondary current. So basically the current which is actually going towards the hysteresis losses, okay, our losses will be lower, and like the current which is going towards this the parallel path, okay, so this branch is actually very small as compared to the load current, okay. So typically this current which is going to this branch is 2 to 3% of the load current, okay. So for simplicity we can also remove this branch, okay. So that will actually simplify our circuit, okay. So like from this circuit like the primary voltage level we can remove this, and also we can remove this, okay. So if we remove this, okay, so basically that makes our circuit more simpler, okay. That will make our circuit more simpler. For example, this is like what will happen here, see, this is my model, okay. Now I'm removing this. So if I remove this, then what will happen, like these two resistance become in series, so total resistance will be Rp over A square into Rs. So that will be the only resistive component, and then I will have only inductive component. This is also in series, this is also in series. So total inductive component reactance will be 3 plus A square times Xs, and here in this side we have the primary side voltage, and in this side we have the secondary side voltage. So that will be the simplified model. Okay, we remove the excitation branch component. Okay, and the same thing will happen like if we go for this case. So again this is remove. So now what will happen? This resistance and this resistance will be added, this reactance and this reactance will be added. Okay, so this will make our circuit more simpler like this one. Okay, so these are the circuit with like and so basically this resistance is what? Summation of the two resistance. Here resistance is what? Equivalent resistance summation of the two resistance. Okay, so just for the simplicity we move the excitation, like even if we keep the just for simplicity, okay, because the current flowing through this is very small, so we are actually neglecting these components. So if we neglect, either we can move to the towards the front of the transformer, or we can remove them also, so that will make our this simplified circuit. Okay, so this is the refer to the primary side circuit with no excitation branch, and this is the refer to the secondary side with no excitation branch. Okay, so these are our simplified circuits. Now the question is, we have developed the transformer model, we have developed the simplified transformer model. So the question is how we can actually find the values. Okay, what is the value of the primary side resistance, what is the value of the primary side reactance. Okay, in the complete transformer model, what is the values of the excitation branch. Okay, the hysteresis losses and the magnetization current and also the secondary side components. So how we can find them? So for that there are two tests which are typically used, and we call them open circuit test and short circuit test. So we use open circuit test for the finding of the magnetization branch component. Okay, so we use the open circuit test to find the RC and the XM value. Okay, and we use the short circuit test, okay, to find the values of the uh, resistance, okay, the equivalent impedance, okay, or like the R equivalent and the X equivalent, okay, reactance. Okay, so to find these two component values, we use open circuit test, and to find the rest of the like the resistor and the impedance component, okay, or equivalent resistance and equivalent reactance component, we need use the short circuit test. Okay, so these are the two test types which are we used for the finding the component values of a transformer. Okay, so now let's have a look what are these tests. So in the open circuit test, what we are doing, we are making the secondary side open. Okay, this is our secondary side, this is open. Okay, so it means no secondary current is flowing. Okay, but even if no secondary current is flowing, still the primary current will be flowing. Okay, so when the primary current is flowing, we installed actually a voltmeter, ampere meter and the watt meter, and we measure the voltage, open circuit voltage. Okay, we measure the open circuit current and we measure the open circuit power. Okay, and we measure these three sides at the input side of the transformer. Okay, so this is the basic things which we have to measure here. Okay, now from this, actually what is happening here, we know that the ratio of the secondary side and primary side is A, right? So but actually what is happening here now, because the secondary side current is 0, right? So it means the primary side current uh, will also be 0 because this is 0. So secondary side current is 0 because of open circuit, primary side current is 0 because of open circuit. So where does the whole current is going? So the whole current is basically going to the excitation branch, okay, in this scenario. Okay, because this is 0, this is 0, now the whole current will be actually going to the excitation branch. Okay, the whole current is going here. This is 0, secondary current is 0, the primary current almost 0, or like we can say that very low value. So basically there is no drop here, there is no drop here. Okay, so all the voltage drop is also coming across this excitation branch, parallel branch. Okay, and the whole the current is also going to the this branch. Okay, so what we can get, we will try to calculate the when we know the current value and the voltage value, so we can calculate the susceptance. Okay, we can calculate the admittance of the circuit. And the admittance of the circuit is what? The ratio of the open circuit current over voltage. Okay, and we know that basically admittance, okay, like the impedance is the resistance plus reactance, right? Similarly, admittance is conductance, okay, plus or minus whatever you say, minus susceptance. Okay, so conductance is what? 1 over R, and susceptance is what? 1 over X. Okay, these are the just like the two terminologies. So from the open circuit current and voltage, we can calculate the admittance of the circuit. Okay, and once we know the admittance value, okay, so the real part, for example, admittance value is coming as 2 minus 3j, for example. So this real part is basically representing the conductance, okay, which is actually 1 over RC. So we can find the value of RC from here, and this value is basically representing the susceptance, okay, or this is actually representing 1 over XM is equal to 3, for example. So we can find the value of the XM. So these two component values can be found. Okay, and like this will give us the magnitude, and if we want to find go for the angle, okay, so the angle we can actually find from the power factor. Okay, so we know that the power factor of a circuit is basically output circuit open circuit power divided by the voltage multiply the current. Okay, so that will be our power factor in this case. Okay, and if you want to find the theta, that will be, so power factor is basically cosine of theta, and if you want to find theta, that will be cosine inverse of power factor. So we can get the magnitude and we can get the angle. Okay, or we can convert that phasor form to the complex form. Okay, and we can get our values. So this is how we actually calculate the uh, admittance and the open circuit power factor, okay, which I have just told you. And to find the rest of the component values, okay, we can find the we can do the short circuit test. So in short circuit test, what we are doing, we make the output circuit short circuit. Okay, now what is happening? And we are measuring again at the input side. We measure the voltage, which is short circuit voltage. We measure the current, which is short circuit current, and we measure the power, which is the short circuit power in this case. Okay, and now what will happen? Because now the current is flowing, okay, secondary current will be flowing. So because of that, we know that we have the ratio of IS over IP is A, so primary current will be flowing. So when the load current is actually flowing, so at that time the current which is flowing through the excitation branch will be minimum, which is around 2 to 3%. Okay, so basically now the current is actually flowing through the primary resistance, okay, primary reactance, secondary resistance, and the secondary reactance. Okay, so we can find the those values. Now what we will do, we will calculate uh, impedance, and impedance is the ratio of the short circuit voltage over short circuit current. Okay, why we are doing, basically impedance is what, as I said earlier, resistance plus reactance. So if we calculate the impedance, we can find the values of the equivalent resistance and the equivalent reactance of the transformer. Okay, that's what we can get from the impedance. And if you want to calculate the power factor in the short circuit test, okay, so again that will be cosine of theta power factor, and that will be power in short circuit divided by the voltage into current into short circuit. Okay, that will be my power factor. Okay, so from this we can get the magnitude, from this we can get the angle. Okay, so if you want to write in phasor form, it will be magnitude with the angle which we are getting from here. Okay, So these two tests we use to find the transformer component values. We will solve the relevant examples in the live session. So this is the example which we will see in the live session. Another concept in the transformer is voltage regulations. So voltage regulation, the meaning of the voltage regulation is that basically if you are making the variation in the load, okay, so then the basically it is the analysis of the variation in the load voltage of the transformer due to the impedance. Okay, you are supplying some voltage and you are getting some variation at the load side. So how we can calculate that? Okay, so for that basically we define a voltage regulation factor, which is actually the secondary side voltage at no load minus the secondary side voltage at the full load. Okay, so this is called actually full load voltage regulation because our reference is full load. Okay, and divided by the full load. So using this formula, we can calculate the voltage regulation of a transformer. Okay, and it helps us to analyze the efficiency of the transformer. Okay, now less voltage regulation means less impedance of the winding. Okay, so because the loss will be across the windings, okay, like the resistor component in the winding, so we will have loss there. So if we are getting low voltage regulation, it means we have the less winding of the transformers, and that is the more desirable thing. We will solve the relevant example about this concept also in the live session. Thank you very much for your time.